Good afternoon. I'm Professor Sever. Today we're continuing Notebook 2 with Part 2, which will focus on linear equations and linear systems. And in this notebook, we will be working on row reduction. So let's begin. Okay, let's consider an example. Now, how do we put a matrix in echelon form? Okay, of course, we do that through the process of row reduction. So let's work an example. So you see, we're starting on this matrix A. Do we have a 1 in the upper left corner? The answer is no, we don't. So the first thing we want to do is switch row 1 and row 4. We do that, and we obtain the following matrix. Now we have a 1 in the upper left corner, so we have a leading entry in the 1, 1 position. What do we need to achieve? We need to have zeros below that entry. And this tells us what our next decisions are. Since we want a 0 in the 2, 1 position, we need to use the row 1 to do it. This is the key for the forward phase, i.e. the key for obtaining echelon form. You use the higher rows to produce zeros in the lower rows. So now we have a 1 in the 1, 1 position. We will use that 1 to introduce zeros below it. Accordingly, we want to do 1 times row 1 plus row 2. Put the result back into row 2. That's a type 3 operation. And at the same time, we want to, in terms of an economy of writing out these matrices, we apply another elementary row operation at the same time. Since we're not applying row 2 to change another row, we're going to use row 1 to change rows 2 and 3. So the second elementary operation for this stage would be 2 times row 1 plus row 3, putting the result back into row 3. And as a result, we obtain the following. Now, we have zeros below our leading entry. That's great. That's what we want. Now, in terms of the echelon process, which is a stair-step process, we move over. Our attention really now is on this 3 by 4 sub-matrix. So now you want, in that sub-matrix, you want a 1, or really a non-zero entry in the upper left corner, which in this case would be in the 2, 2 entry of the entire matrix. Now, I could use scaling, okay, but I want to show how you can do it directly with type 3 elementary row operations at this stage. By the way, the echelon form is not unique. That means each of us can apply a different series of elementary row operations to achieve an echelon form. So if we were to reduce this, you may not make these decisions. You might make other decisions. And we could scale, if you notice, we could scale row 2 by a half and get a 1 there. But for illustration, I'm going to show how it can work if you don't do that. So I'll multiply row 2 by minus 5 halves and add that to row 3. That would produce a 0 in the 3, 2 position. Accordingly, I will multiply row 2 by 3 halves and add that to row 4 as my second operation. And as I do that, you obtain the following. And I'm leaving the arithmetic to the reader. So what you should do is you should pause the video at this stage and do those computations. Let me do them verbally so you could see what we get. Minus 5 halves times 2 is minus 5. Minus 5 plus 5 is 0. That's how we get the 0 in the 3, 2 position. Then we get minus 5 halves times 4 is minus 10. Minus 10 plus 10 is 0. That's how we get a 0 in the 3, 3 position. Minus 5 halves times minus 6 is it's 15. When we add that to negative 15, we get 0. And then we have the same operation, since it's the same numbers, for the corresponding 5th entry in that row. So try it yourself on row 2 and row 4, and you'll see that you get the following matrix. Now, what is our next decision? Well, we see a row of zeros. In the third row, we need that to be below any non-zero row, so I think we should do a row switch. Let's interchange rows 3 and 4. Doing so yields the following. Okay, so now we have our 0 row. We've done the row switch. This matrix is the result of that last row operation of interchanging rows 3 and 4. So now what do we want to do? We have echelon form. This matrix is in echelon form. So one thing we can do, we could stop here, but for effect, I'm going to kind of prep it for the next phase. Let's make the leading entries a 1. It's not necessary. I'm just doing this for illustration. Technically, I could stop here, right? Once the matrix is in echelon form, the leading entries become the pivots. And that was the second part of our problem, locate the pivot columns of A. So we have a pivot in the first column, we have a pivot in the second column, we have a pivot in the fourth column. Therefore, columns 1, 2, and 4 are pivot columns of that matrix. Now, we don't know whether this matrix is augmented or not. We weren't given that information. Therefore, it would not be appropriate to assume that it is. Okay, so as a last step, just for illustration or for fun, we can continue. And what I'm also indicating is that the echelon form is not unique. I'm going to get a different matrix that's row equivalent to the first, and therefore it's row equivalent to every one of them, and hence the original. It will still be in echelon form, but it'll have an added benefit, so to speak, that the leading entries or pivots will be a 1. To achieve this, I multiply row 2 by a half, that's scaling, and I also multiply row 3 by minus 1/5. We obtain the following matrix, which is also in echelon form. So in this example, we have shown two matrices that are row equivalent to the original matrix, both of which are in echelon form. Therefore, the echelon form is not unique. Now, is this matrix in reduced echelon form? No. The entries above the pivots are not 0. And if we were to put the original matrix in reduced echelon form, we would have 3 steps to go to do that, putting zeros here, here, and here. And as I said, to reiterate, we have 3 pivot columns, columns 1, 2, and 4, because those are the columns that contain the leading entries. Now remember, when the matrix is in echelon form, the leading entries are then referred to as pivots. Let's go back. Look at the first matrix. What are the leading entries of that matrix? Well, the leading entry in the first row is in the second position, i.e. the 1, 2 position. The leading entry in rows 2, 3, and 4 are in the first column. Those entries are in the 2, 1, 3, 1, and 4, 1 positions respectively. Now, are those pivots? Would we say that there's a pivot in the second column and first column? Not by this logic, because this matrix is not in echelon form. Therefore, we cannot say that the leading entries are where the pivots would be. And also, you would never have 2 pivots in the same column, right? That's a consequence of that stair-step aspect, part B of the row echelon form definition. Let's move on. Okay, I've alluded to this theorem, existence of an echelon form. So first off, you can always put a matrix in echelon form. That's what that theorem says. The theorem actually says each matrix is row equivalent to an echelon matrix. And that means it's row equivalent to a matrix in echelon form, which says if we're given up any matrix, we can always put it in echelon form. And by put it, that means obtain a matrix that's row equivalent to it, which is in echelon form. And by my last example, I showed the echelon form. In the previous example, as I'm indicating here, we had 2 matrices that were row equivalent to the original matrix, and both of those matrices were in echelon form. And therefore, the echelon form is not unique. Okay, now, uniqueness of the reduced echelon form. So the theorem reads, each matrix is row equivalent to one and only one reduced echelon matrix. So let's think of it this way. If you're given a problem, if I have a class of 20 students, I could put a matrix on the board and say, let's find a matrix that is row equivalent to this matrix that's in echelon form. Another way to say that is to say, put this matrix in echelon form. So each of those 20 students could get a different answer, and they could all be correct. Why? Because the echelon form is not unique. However, if I were to say to the class, let's put the matrix in reduced echelon form, which means find a matrix that is row equivalent that is in reduced echelon form, then we would all get the same answer. All 20 students, if they did the problem correctly, would obtain the same answer. Why? The reduced echelon form is unique. And that's what these 2 theorems are saying. And this concludes part 2 of this notebook series. In part 3, we will begin by row reducing a matrix to reduced echelon form and continue the lesson in this series. I'm Professor Sever. Thank you for watching. I hope you enjoyed Notebook 2, Part 2.